Hello everyone, my name is Wenkai. Thanks for letting me here. Today my topic is load optimization in reconfigurable networks, algorithm and complexity of flow routing. This is joint work with Klaus Foerster, David Fuchssteiner, Stefan Schmid, all of us from University of Vienna. Nowadays, data centers have become a vital infrastructure of our society. In order to cope with the rapid increasing amount of traffic inside the data center, improving the top-rack connectivity is a pressing issue. Current data center design, such as the popular factory topology, focus on improving all-to-all throughput by increasing the bisection bandwidth. On the other hand, as soon as the traffic becomes more structured, the throughput in this data center suffers. However, recent studies have shown that the traffic inside the data center is often not uniform all-to-all, but rather creates traffic hotspots that change over time. In some example, for example, the right figure shows even up to 99% of pairs exchange no traffic at all. This fact invokes the need for a design paradigm shift. Currently, industry provides two types of switch, the circuit switch and packet switch. The circuit switch usually is optical, is faster with high bandwidth. The connection between ports can be adjusted dynamically. On the other hand, the packet switch usually is electronic, with a low bandwidth. The connection of links are fixed after deployment. Let's have a closer look at the physical layer of the circuit switch. So it contains a set of reconfigurable links, but it's not an all-to-all switch, just one connection per port. So we have to select a matching to connect the ports. For example, here and here is a matching. So to take advantage of these two types of switch, people propose the hybrid architecture for data center. For example, Hinos is proposed the SIGCOMM 2010. So my idea is to adjust the topology dynamically for variant demands, such that the big floors can go through this circular switch, and the small floors can go through this packet switch with low bandwidth. So such reconfigurable data center networks really attract a lot of research interest in past years, and many more works are still under construction. Let's have a faster review of routing models. So for each demands, here for example A to E, unspeakable routing model request there's only one path from source to destination, but a splittable routing model allows multiple paths from source to the destination. And in reconfigurable data center, we have two more routing models, segregate and non-segregate. For each demand, here for example A to E, segregate only can send the flows on the path consist either static link or reconfigurable link. But the non-segregate model allows flow transfer on the passes consist of both static and reconfigurable links. Now, by combining these four routing models we introduced just now, we obtain four routing models in reconfigurable networks. We list them in the table. For example, the splittable and segregation model is abbreviated as SS. We will discuss these four routing models in our problems later. So let's focus on definition of our problem. It's called the load optimization reconfiguration problem. We are given a routing model discussed just now. We have a demands matrix, and we have a reconfigurable network. It contains static network. It shows here. Meanwhile, we have a set of reconfigurable links, and we have a circular switch. Recall, in this physical layer, you have to select matching from set of reconfigurable links. So with the given input, our task is to compute a proper matching to obtain a hybrid network, such that then we need to compute an optimal routing for the given demands and the routing model in this hybrid network, such that the maximum link load in this hybrid network is minimized. So this is our problem. Let's give an example to help you understanding our problem. So this is our input reconfigurable network. So here only 4 switches connected to circular switch. Let's represent this by these nodes. So for this 4 switches, we just abstract it into one node. And the circular switch, we represent this kind of reconfigurable links by blue dotted line. So we need to find a matching from these reconfigurable links. We can abstract this problem into this topology. Here, red dotted line is reconfigurable links, and here is static links. So we need to find a matching from these reconfigurable links. Okay, so we are given the demands as follows. Before doing any reconfiguration, we can compute this load on the static links. Here the max load is 20. So by our intuition, okay, A to B is the highest demands. That's why perhaps we should choose reconfigurable link A to B. If choose A to B, then to choose the matching D to E is also chosen. So by configure A, B, and D, we obtain the hybrid network. By after computing this optimal routing, we found that the max load is 12. But actually, for the same demands, the optimal matching is choose DB and AE. After configure AE and DB, we obtain such a hybrid network. By computing this optimal routing, then we found the max load on this hybrid network just 10. By this example, we know it's quite critical to choose the right matching to obtain this hybrid network. So after understanding our problem, let's come to the complexity of the problem. Unfortunately, when a given static network is a tree with height equal to 2 or larger, our problem already is strongly NP-hard for these 4 routing models. It can be proved by the reduction from a 3-partition problem, especially the UN routing model is already weakly NP-hard. When this input static network is a tree with height 1, it means a star network. And it can be reduced from 2-partition problem. We note that this problem is not hard anymore if this demands quantity is not big. So how can we do under such a hardness result? Okay, so fortunately, fat tree and the clause in data center usually they implement something called a non-blocking interaction in the above layer. It means for above layer, you can think it's like a cross-bar switch. It's plenty of connectivity and bandwidth. That's why it can be further abstracted as a packet switch for whole above layers. Then the bottleneck just occurs this layer. This is what we will focus. So we can rewrite this topology into this structure. Actually, static network become a star with a packet switch. So actually, this topology already considered in the previous work. Now, let's introduce our optimal algorithm for this simplified problem under this non-blocking property. So we will consider the same problem. Let's assume the minimized max load is theta, and we use the set S to store all the possible value for theta. Of course, before the configuration, the load on each of the static link will be in S because each of them can be our final theta. So next step, we will first compute the set C. Now, in this slide, we introduce some useful observations. If a reconfigurable link is selected in a matching, for example, AE, it's defined a triangle ACE. And then for any demands from a node outside the triangle to the node inside the triangle, for example, B2E, we know no matter what's the structure outside the triangle, then we know the flows for this demands B2E will always go through C before he enters the triangle ACE. Reversely, if it demands from the triangle from node inside the triangle to a node outside the triangle, its flow always goes through C at first before he leaving the triangle. After understanding this useful observation, we realize the minimized maximum load theta can be obtained by computing the local optimal load for each of this triangle. Then, what's the local demands for each of this triangle? So let's see here. So for demands to E, we can propagate as demands from C to E. Then the demands from E to nodes outside the triangle can be propagated as the demands E to C. Here, by deploy, we define our local demands for each of triangle. We know our routing model, we have local demands deploy. Then we can find the optimal routing in constant time in each of the triangle. Let's max load in this triangle as a delta I. Then after computing each maximum load for each triangle, we know all the possible value for the theta. We already have our theta S. Then by the binary search in the theta S, we can find the actual theta. For each specific theta, we will mark each node target if its link load is larger than theta before the reconfiguration. Because since it's already have load bigger than theta, you must be put one reconfiguration link to include this target node. After that, for each specific theta, we define a useful reconfigure link, EPRI. What is the useful reconfigure link? For each of a triangle, we know the maximum load delta I, and if this delta I is smaller or equal than theta, then we call this reconfigure link AE is useful because they can turn the node lower than our bound. So now for each specific theta, the target node and the useful reconfigurable links are known. Then we can construct a new graph GPRI, only use this useful reconfigurable links. So we can find a matching in GPRI to cover all the target nodes by maximum weight matching. If we can find such a matching, it means in this hybrid network, all the link load will be small equal than theta. We mark that the running time is log v multiple the running time over maximum matching. Here we do some theoretical analysis of performance. We know the maximum load can only be decreased by half after adding these reconfigurable links, because for each pair of demands, there are at most 2 edge disjoint passes between them. And our optimal algorithm definitely achieves this lower bound. Meanwhile, for the max matching algorithm, we found for some examples, the max matching can only decrease max load by an arbitrary small value. Now we come to experiment evaluation phase. So we do our experiment based on the data from the Facebook. So we compare our algorithm with two heuristic algorithms, max matching and Firefly. Firefly is a greedy algorithm. We use the max load before adding any reconfigurable links as our baseline is showing here. And it's clear our algorithm can reduce the max load almost by half, which match our theoretical analysis. And these two heuristic algorithms can only decrease this baseline a little bit, especially for max matching. Sometimes it does not make any sense. Then we come to evaluate our running time. Theoretically, greedy algorithms have a linear running time with respect to number of nodes. Max matching by Bluetooth, they have this kind of running time, and our algorithm has a log v multiple running time over max matching. Log v is because of the binary search. By comparing this experimental result, we found it's match our theoretical analysis very well, especially our algorithm is very close to the running time of the max matching. Finally, thanks for your listening and welcome your questions.